This is JSteele's Precalculus, Section 9.3. We're going to talk about systems of linear equations in several variables. So the past two sections we talked about systems of linear equations with two variables, but now we're going to add a third variable. So linear equations are just in the form like 8x plus 9y minus w equals 6, where there's only one exponent per term, and the variables on the exponents are all 1. So these are all linear equations. In linear equations, we are able to solve for variables. If we have 3 unknowns, we need three different equations to solve. If we have 2 unknown variables, we need two equations to solve. And if we have 4, we need at least four equations, and so on. So that's for linear equations. We can also have nonlinear equations. So this is in the form like square root of c minus 7y plus x squared equals -9. We are not able to solve for this because exponents on the variables must have a value of 1. Since the square root of c, we have an exponent of 1/2, and the 2 on the x tells us we are not able to solve. And this is just because we will have different domain restrictions. We would end up with positive and negative numbers when taking the square root of something. So it's just it's a little more difficult to solve for exponents that are numbers other than 1. Another scenario is if we have 2 variables multiplied. Notice we have an x times y plus 8z equals 7. Since we have x times y, we are unable to solve for this nonlinear equation. So this tells us that variables cannot be multiplied. So we will just be dealing with solving for linear equations, but with more than 2 variables. So taking a look at graphing in 3 dimensions, we have the x-axis and the y-axis, and the new thing we are going to introduce is the z-axis. This can be drawn in different positions. So looking at the example to your right, the x and y axes are the same as we always see them. And then the z-axis, it's hard to see in the picture, but it's really the axis that points straight out at you. The graph of a point, the one point is called an ordered triple. So rather than an ordered pair, point in the form x, y, z is called an ordered triple. The axes divide spaces into 8 regions called octants. Since there's 8, that's where we get that oct from. So the graph of an equation, the graph of a linear equation in the form ax plus by plus cz equals d, is referred to as a plane. This graph only shows the part of the plane in the first octant. So the graph to your right, and the first octant is really the only one that we can visualize. The only way we'd be able to see the other octants is if we had a 3-dimensional graph in front of us. It also shows the x-intercept, the y-intercept, and the z-intercept. So the graph of a system of 3 linear equations, this graph consists of 3 different planes. So the points that are 3 planes have in common, if there are any, are the solutions to the linear system. So before, when just dealing with an x and a y variable, the intersection point, whether they intersected at 1 point, 0 points, or no points, or 1 point, 0 points, or infinitely many points, that told us the number of solutions. So since we have since we have 3 variables per equation, instead of having lines, we're going to have planes. So wherever these planes intersect is the number of solutions. So looking at the first the first example, these three planes intersect at one single point. You can see it right in the middle. So this has one solution, exactly one solution. Looking at the picture to the right of it, it has infinitely many solutions because the planes intersect. They intersect on the line or in the same plane. So what I boxed in blue is the plane where the three planes intersect. And the bottom three examples are examples of three planes having no solutions because they share no points in common. Even though there could be two planes that intersect, in order for you to have a solution, you need 3 points of intersection. So let's take a look at an example. The triangular system, we're going to solve a system by using a technique called back substitution. So we use back substitution when looking at our three equations. If we have one equation that has all three terms, another equation with two variables, and a third equation with only one variable, that's when we are allowed to use back substitution. Notice that we can easily just divide by 3 in the third equation, and we end up with z equals 4. So since we get z equals 4, that's our first step. Using the second equation, since there's only 2 unknowns and we already know what one of them is, first, to solve for our second variable, we can take 2y minus z, which we know z is 4, so 2y minus 4 equals 2, and just solve for y. So start off by adding 4, so we're left with 2y equals 6, and then dividing by 2, we have y equals 3. And now since we know what z and y both are, we can use both of those and plug them into the very first equation. So then our third step is just plugging in our known values. We have x minus 2 times 3 plus 3 times 4 equals 10. 2 times 3 is 6. We have x minus 6 plus 3 times 4 is 12. So we have x minus 6 plus 12 equals 10. X minus 6 plus 12 can simplify to x plus 6 equals 10, and then subtracting 6, we're left with x equals 4. So now we have our x, y, and z, so writing our final solution in the form x, y, z equals 4, 3, 4. So again, the only time we can use back substitution is when we have one of our equations with 3 variables, one equation with 2 variables, and one equation with 1 variable. It's the only time we're able to use back substitution. Solving a non-triangular system, we can solve by reducing the system of 3 equations to a system of 2 equations by using the method of linear combination. So your goal when using linear combination is to hopefully either add or subtract two of your equations to eliminate a variable. So looking at the first and second equation, if we add those two together, we would get rid of the x variable. So adding those two together, we have x plus 3x, which is 4x. Negative y plus y, we don't have a y term. And then 2z plus 5z is 7z. So we have 4x plus 7z. Equals then 2 plus 8 is 10. And then looking at the second and third equation, we want to, again, eliminate that same variable. We need to get rid of the y's. So if we add the second and third equation, we will also get rid of the y term. So 3x plus 2x is 5x. Our y terms cancel, and we are left with then 5z minus 2z, so plus 3z equals 1. So our first step was to eliminate that y term. Now we're just going to use these two equations and solve it as we would a normal elimination or substitution method for a system of two equations. So if we multiply the top equation by 5 and the bottom equation by -4, we can get rid of the x term. And this becomes 20x plus 35z equals 50. And the bottom equation becomes -20x minus 12z equals -4. So then adding our terms, our x's will cancel, and we are left with 23z equals 46. Dividing by 23, we're left with z equals 2. So once we have z equals 2, we now will use back substitution to first get x, and then get y. The reason we need to first get x is because these two equations both have x and z in them, so we can pick one of them and plug in our known z value. So just using that top equation, we will have 4x plus 7z, which we know z is 2, so 7 times 2 equals 10. 4x plus 14 equals 10. Subtracting 14, we have 4x equals -4, and then dividing by 4, we have x equals -1. So now once we have x equals -1, we can use that and plug it into one of the equations from the original. Again, I'm just going to use the first equation, so we'll have -1 minus y plus 2 times z, which we said z was 2. So 2 times 2 equals 2. So -1 minus y plus 4 equals 2. Combining like terms, we have -y plus 3 equals 2. So solving for y, we need to first subtract 3. We're left with -y equals -1. Dividing by -1, we have y equals +1. So now we have an x, we have a y, and we have a z term. So since we have an x, y, and z term, we can just substitute in our values. Since x is -1, y is +1, and z is 2, our ordered triple will be -1, 1, 2.